Hello friends, my name is Akshans and welcome to CADDD Academy. In this lecture we will study the root locus technique, and the root locus diagram is made to get the closed loop stability of the system. Root locus is also the best method to find the relative stability. Okay, so in this lecture we will be drawing the root locus diagram for different types of systems, and we will study all the formulas, all the requirements which is needed to draw the root locus diagram. We will study the root locus technique completely in this lecture. So first of all, let's see the formulas which is required to draw the root locus diagram. And the first formula is what? Angle of asymptote. Okay, so to get the angle of asymptote, what we do is we represent that with the theta, and which is what? 2 into q plus 1 divided by number of poles minus number of zeros into 180 degrees. Okay, where q is what, guys? 0, 1, 2 and up to p minus z minus 1. Okay, this thing minus 1 up to there, this q goes. Okay, and the second thing we calculate is what? Centroid, and which is what? Alpha, and that is sum of real part of poles. We will understand all these formulas by drawing the root locus diagram. There it will be more clearer to you. So real part of poles minus real part of zeros divided by number of poles minus number of zeros in the system. And the next thing which we need to draw the root locus diagram, and that is what? Breakpoint. Okay, so for that we differentiate the system's transfer function by the s, and we take k is equal to 1 there. Okay, k is what? The system gain. And then the roots are the break points. Okay, and the next thing which we will do is what? Angle condition, and that is what? Angle of the transfer function at s is equal to at some point which is equal to 180 degree plus or minus 180 degree. If this angle's condition is satisfied, if satisfied, then this point s is equal to, we will put some points location here, and this point is on the root locus branch. And the next thing is magnitude condition. So in magnitude condition, the magnitude of the transfer function at s is equal to that point. If it is equal to 1, then we will get the value of the system's gain k at point which is this point. Okay, so now done with the basics, and understand all the things by doing the questions. So we have to get the k value at minus 5 plus j5, and where the transfer function given is gh of s, that is k by s into s plus 10. So this is the transfer function given, and we have to calculate the k value at -5 plus j5. So first of all, we have to check that is this point lying on the root locus branch. If it is not lying on the root locus branch, then we cannot determine the k value. So how we will know that this point is lying on the root locus branch or not? So yes, this angle condition. So angle condition, we will apply the angle condition, and for that we have to get the angle of transfer function. That will be what? Angle of k divided by, we will put the s value, this thing, that will be what? -5 plus j5, and here what we have? -5 plus j5 plus 10. So after solving this, we will get what? Angle of k, and the angle of -5 plus j5 into the angle of, that is what, 5 plus j5. Okay, so now we can get the angle of this thing by tan inverse 5 by 5 and tan inverse 5 by 5, but we can solve this further, and k by -50, because this is what? A minus b, a plus b. Okay, so we know that a plus b into a minus b, which is what? A square minus b square. So by using this, we will get the value -50 here. Okay, so angle of k is a constant here, and angle of -50, this will be what? Plus minus 180 degree. How? Because we know that this is the imaginary axis and this is what? Real axis. So this -50 is lying on the negative real axis, and which is what? Either -180 or plus 180. So this -50 is what? Plus minus 180 degree, and this angle of k is just a constant, and we will take generally it as the positive value. Okay, let's say k is lying here somewhere. Okay, so k will have angle equal to 0 because this is a 0 degree line. So we can say that the angle we are getting is what? If this thing will go in the numerator, then this will be what? Minus plus 180 degree, and we can see that angle condition is getting satisfied. We are getting the plus minus 180 degree as the answer. So angle condition is satisfied, so we can say that this point is lying on the root locus branch. And now we will find the k value by using the magnitude condition. Okay, so now we will get the magnitude of transfer function, that is what? K by s into s plus 10, and the magnitude of this, and at s is equal to -5 plus j5, we will equate this thing equal to 1. What we are using here is magnitude condition, not that what you are thinking. Now put the s value here. What we will have here is -5 plus j5 plus 10, and we have to get the magnitude of this. So here we will have what? -5 plus j5 into 10 minus 5 plus j5. So this will be what? -5 plus j5, and here it will be what? 5 plus j5. So When we get the magnitude of this thing, we will get what? K by minus 50 as before, and magnitude of this is what? We have equated that to 1 here. So from here we can get that K by 50, because this minus is contributing in angle only. The magnitude is just K by 50, and which is equal to what? 1. So from here we got the value of K, and which is what? 50. So at the point this the value of the system's gain K is what? 50. So friends, now we know how to use the magnitude condition and the angle condition. Now we will take a transfer function and we will draw the root locus diagram for that transfer function. So the given transfer function is what? K s plus 10, and in denominator we have s square into s plus 1. Okay, firstly we will calculate the angle of asymptote. Okay, so the formula for that is what? 2q plus 1 divided by p minus z into 180 degree. Simply we can write it as 180 degree divided by number of poles minus number of zeros, and that will be what? Here number of poles minus number of zeros is what? Here we have 3 poles. Okay, 2 at the origin and 1 at minus 1. So we have 3 poles and 1 zeros only, which is at minus 10. So 1 0. Okay, so we have 3 poles and 1 0. So 3 minus 1 is what? 2. So 180 divided by 2, which is what? 90 degree. For this thing, what we will do is multiply it with 1. After that, another odd number. After 1 we have what? 3. We will go for 5, 7, 9 and so on, but here we have only p minus z as 2. We will do this multiplication only twice. Okay, because this is what? 2. So here what we will have is 90, and 90 into 3, that will be what? 270. So these two are the angle of asymptotes for this transfer function. Okay, now we will calculate the centroid, which is denoted by alpha. And for centroid, what we have studied, that we have to put the location of real part of the poles. Okay, so which is 0 for this one. For another one, 0, because we have 2 poles at the origin, and we have 1 pole at minus 1, so minus 1. So this is what? Real part of poles and minus real part of zeros. So 0 is at minus 10. So what we will write here is minus 10, and we'll divide by p minus z, which is what? 2. So from here we get that 9 by 2 is the centroid of this transfer function, which is what? 4.5. So now we will draw the root locus. Like we have at 4.5 we have what? Centroid. Okay, and this is centroid, and what we have here, we have 1 pole at origin, another pole at origin. So we have 2 repeated poles at the origin, as this system is what? Type 2 system, because 2 poles at the origin. So this is what? Type 2 system. And we have 1 pole at minus 1, and we have 1 0 at minus 10. So this is what? Real axis, and this is what? Imaginary axis. So this is the location of centroid, and these are the angles of asymptote. So at centroid we will draw the angles of asymptote. So this will be 90 degree like this, okay, and this will be what, 270 degree, okay, and this is what, 90 degree. So we have these two are the angle of asymptote, and this location was centroid. So at centroid we will draw the angles of asymptote. And now what will happen here, now what will happen, that as k increases to infinity from 0, okay, so as k is moving from 0 to infinity, okay, now at k is equal to 0 these poles are at same location, okay. As we will keep increasing the system gain k, okay, then what will happen, this pole will get a waypoint, they will get what, breakaway point, and they will leave the real axis, okay, they will strike together and they will leave the real axis. One will go in the direction of first angle of asymptote and another will go in the direction of second angle of asymptote, okay. So this angle is what, 270 degrees, and this angle is what, 90 degrees, okay. So as k increases from 0 to infinity, this pole goes from this path and reaches at 0, which is at infinity, okay. We don't know the location of this 0, okay, and this 0 is also at infinity. And what will happen with this pole, this will be the root locus branch. How we decide the root locus branch? So firstly we will keep our pen here and we will see right to this point, and at right to this point we don't have any poles and zeros. From right to this point we don't have any root locus branch, okay. We will move further, and from this to right side we don't have odd number of poles or zeros, okay. So this will also not be the root locus branch. From here onwards, okay, in this direction, what if we kept our pen here, then from right side we have 3 number of poles, where 3 is an odd number. So we can say that from here onwards it will be a root locus branch. But we'll move further from this, we will have 4 things, 1 2 3 4, okay. So we have 4 number of zeros and poles, so will not be this will not be the root locus branch, okay. So from here we won't have any root locus branch, because from here to right side we have only 2 poles, we need 3 or only 1, okay. From this point we have 3 numbers of poles here, so we can say that this point is lying on the root locus, okay. So now what will happen here, that this pole at k is equal to 0, this pole will be at this location only. As k will increase, this pole starts moving this side, and this pole moves this side, okay. And what will happen, at k is equal to infinity, this pole will reach to this 0, okay. This pole and 0 will be at same location at k is equal to infinity, okay. So similarly what happened here, that at k is equal to 0 the pole location, both poles location was this, and at k is equal to infinity this pole reaches at these zeros, okay. So at k is equal to infinity these both poles reaches at these zeros. So this is the basic fundamental root locus diagram. So now we can get the k value at any point. Okay, we can get the k value at any point here from the root locus diagram. We have seen that how to get the k values in any root locus diagram. We got that in previous problem by using the magnitude and the angle condition. Okay, so this was the general root locus diagram for this transfer function, and we will draw another root locus diagram for another different type of transfer function. Okay, so now I am taking another problem, and which is what gh of s is what k s plus 2 s plus 4 and s cube. So this is the type 3 system because we have 3 poles at the origin. So for this system we have to find the breakpoints location. Okay, so we will find the breakpoints location. So to get the breakpoints, what we will do is, as I have told you in the basics, that to get the breakpoint, what we do is we differentiate the function gh of s with respect to s with k is equal to 1. Okay, and we will equate this equation equal to 0, and the roots will be breakpoints location. Okay, roots will be breakpoints location. So we have what, as a transfer function we have what, s plus 2 s plus 4 divided by s cube, and we have taken k is equal to 1. Okay, so we know that if we differentiate a fraction with respect to a variable which will be what, second function as it is, first differentiation minus first as it is, second function's differentiation, where second function is what, v, and the first function is what, u, and the function at the denominator we have to make its square in the denominator. So applying the same rule here, what we will have, that second function as it is and differentiation of this thing will be what, s square plus 4 and 2 which is what, 6, so 6s, and 4 into 2 which is what, 8. So this is at the numerator. So second function as it is and differentiation of first function which will be what, 2s plus 6, and we will subtract this like this. So we will subtract this from first function as it is and differentiation of second function, and that is what, 3s square. We will divide the whole thing with the denominators square, and we will equate this is equal to, we will equate this to 0. So if this thing goes that side, that will be what, 0. So after solving the numerator we will get an equation which will be what, 2s4 plus 6s cube minus 3s4 minus 18s cube minus 24s square is equal to 0. So if after solving this will be what, minus s to the power 4 minus 12s cube minus 24s square is equal to 0. Taking this minus sign at this side, this whole equation will be positive, and at the same time we are taking the s square common from all the terms. So what we will have, that 12s plus 24, this will be equal to 0. So from here we can say that s is equal to what, 0 0. Okay, here we have s square, so 0 0, two roots will be 0 0, and the other two roots for this equation, and that will be what, minus 2.53 minus 9.46. We can calculate these roots by minus b plus minus b square minus 4ac divided by 2a, or we can simply use the calculator for this. And if the calculator is not allowed to your exam, then you have to use this formula and get these both roots. And after that, what we will do is we will draw the root locus diagram. Let's see how it will be. So this is what real axis, this is what imaginary axis. This is the transfer function, and by seeing the transfer function we can say that we have three poles at the origin, 1 0 at -2 and 1 0 at -4. Okay, so three poles at origin, 1 0 at -2, 1 0 at -2 and 1 0 at -4. Okay, so this is the pole 0 location. Okay, so at this point we have 0, which is an even number. Okay, so for 0 we don't have this as the root locus branch. After moving this side, moving left side, then what we will have at this point, what we have, three numbers of poles or zeros at right from this point. So this is what a root locus branch, because it is what, an odd number. Okay, so this is the root locus branch. Getting up to this point, what we will have here, we have four things. We have three poles and 1 zeros from right to this point, and hence we will not have root locus branch at this area. After here, after moving up to here, what we will have, three poles and 2 zeros from right of this point, and 5 is an odd number, so we can say that this negative real axis up to -infinity will be a root locus branch. Okay, so we have drew the root locus branches. Now we will draw the root locus diagram. At k is equal to 0, all the pole location will be at 0 only. Now at which location we have breakpoints. Keep the thing in your mind that breakpoints always lies on the root locus branch. Okay, so this 0 and 0, is this on the root locus branch? Yes, this point is including the root locus branch. Okay, these both points are valid breakpoints. Okay, now what we have, this breakpoint which is at 2.53. okay, minus 2.53, which will be somewhere here, and this breakpoint is not lying on the root locus branch, so we can say that it's not a valid breakpoint. At this point, okay, minus 9.46, this will lie somewhere here, and this is on the root locus branch, so we can say that this transfer function has three valid breakpoints, which is at 0 0 and minus 9.46. so basically it's two breakpoints only. Okay, with first one is at 0 and the second one is at minus 9.46. okay, so now we will calculate the angle of asymptote and the centroid location. Okay, so that we can draw the root locus diagram. Okay, so for angle of asymptote, what we will do is 180 divided by poles, number of poles minus number of zeros. So we have what, three number of poles, and two zeros. Okay, so 3 minus 2, which will be what, 180. We will multiply it with odd numbers, and we will multiply it with odd numbers only once, because 3 minus 2 is 1, p minus z is only 1. Okay, so we have what, 180 degree as the angle of asymptote. Okay, now we will get the centroid location, and that will be what, we have three poles at the origin, so 0 plus 0 plus 0, so these are the location of poles, minus we have two zeros, and one is at -2 and another one is at -4, and we will divide this thing by 3 minus 2, which is what, 1. Okay, so what we have as the centroid, which is what, 6. So at 6 we have what, centroid. Okay, this is what, centroid, and the angle of asymptote is what, 180 degree, just this line. Okay, this is 180 degree, like this. Okay, so 180 degree is the angle of asymptote. And now we will draw the root locus diagram. So what will happen here, that we have 3 poles here. So these 3 poles will maintain the equal angle while leaving the real axis. So this will go like this will go like this will go like this. So one of the pole will reach at this 0. Okay, one of the pole will reach at this 0, and this angle will be what, 120, this angle will be 120, and this angle will be what, 120. So whenever we have multiple poles at the same location, then while leaving the real axis, all the poles maintains the equal angle, which is 120 degree here. When we have 3 poles at the same location, so they will maintain equal angle between them while leaving the real axis. So these 3 poles are maintaining 120 degrees angle, and these poles will move like this as the k will increase. K is what, system gain. As the system gain will increase, this pole will move like this, and this one will be here. At the same time, this pole will also reach at this point, and this point will be what, break in point, because both poles are getting into the real axis. This location will be what, break points location, that is what, 9.46. okay, sorry, 46. And this 0 was the break away point. Okay, this 0 was the breakaway point, because these poles are leaving the real axis. So this is the breakaway point, and this is what, break in point. Okay, now after reaching at the real axis, this pole will strike with each other, and one pole will move at this direction. Okay, and another pole will move in this direction. Okay, at k is equal to infinity, this pole will reach to the 0, which is located at infinity. We don't know the location of this 0. Okay, so this is the whole pole 0 plot while we are increasing the value of system gain k from 0 to infinity. So at k is equal to 0, what we have, these poles are at 0, these zeros are at these points. Okay, as k will increase, this will move like this will move like this, one pole will move towards this 0, and these two poles will make a break-in point here, and one of those two poles will go this side and another one will go this side, and will reach at this zeros, and will reach at this 0 at the k is equal to infinity. So this was the root locus diagram for this transfer function. Now the last thing which is left in the root locus technique is what, angle of departure and the angle of arrival. Okay, so in the basic, I haven't explained the angle of departure and the angle of arrival, so I am telling that now, and which is this phi d is what, angle of departure, and which is what, 180 degrees plus angle of the given transfer function at positive imaginary pole. Okay, positive imaginary pole, and where this pole is what? A complex pole. Okay, so angle of departure and the angle of arrival is always calculated for the complex poles or zeros. Okay, so this is what angle of departure, and angle of arrival is what? 180 degree minus angle of GH at this same thing. Okay, so now we will take a problem for this and we will solve that and we'll get this thing very clearly. So we have to calculate the angle of departure for the transfer function, which is given as k into s plus 2 s plus 4. Okay, this is what? 4, and s square plus 2s plus 2. So this is the transfer function and we have to calculate the angle of departure for this transfer function. So for this, by using the minus b plus minus b square minus 4ac by 2a, we will get what? We will get the roots of this equation, or simply we can do s square plus 2s plus 1 is equal to 0. Okay, and what will happen? S plus 1's square, okay, is equal to what? Minus 1. This whole thing is what? S plus 1's square. Okay, now from this we can say that minus 1 here plus minus j1, so these both are the roots of this equation. Okay, or if you didn't got this concept, then you can use this formula simply. Now let's draw the rough root locus diagram. Okay, so we have two poles at minus 1 j1 and minus j1. So okay, like this we have what? Two zeros, one is at minus 2 and another one is at minus 4. Okay, this is the skeleton of root locus diagram. What we will do now is we will get that we know the formula of angle of departure is what? 180 degree plus angle of GH. Okay, so we will get this thing first. So angle of GH at pole, and we will take generally positive pole, which is what? Minus 1 plus, we will take positive imaginary complex pole, and which is what? Minus 1 plus j. Okay, now we will get the angle of transfer function at this location. As k is the constant, it will lie on the real axis, and somewhere here we will take k as the positive value, so it will lie somewhere here. So k has what? 0 degrees. Okay, because this is what? A 0 degree line. Okay, so k has angle of 0 degrees. Not writing that. Now we are putting the value of s, which is what? Minus 1 plus j plus 2, this thing. Now s value we are putting here also, but we have minus 1 plus j plus 4. Now we will put the s value here also, and we will do it like, we know the poles are this, so we can write this equation as what? S minus 1 plus j, s minus 1 minus j. So we will write this thing in the denominator, and what we will have? if we will subtract this thing, s is equal to what, this is also the s is what we are taking, s is what, this thing, and same thing is here also, so s minus this thing will be 0, so we are not writing this will lie on the angle 0 line, so we are not taking this because adding or subtracting the angle 0 is not gonna give any effect on the angle of the transfer function, so we will take this thing only. So s value is -1 plus j minus 1 minus j, this thing. So we will solve this and we will get what, 1 plus j and 3 plus j divided by what we have in the denominator, that is what, j2. So we will get this whole thing's angle. So angle of this thing is what, tan inverse imaginary term which is 1 and real term which is 1, okay, plus tan inverse imaginary term which is what, 1, okay, and the real term which is what, 3, divided by 90 because j2 is what, lying on the 90-degree line, this is what, 90 degree, okay, so j2 will lie somewhere here, so this is what, 90 degree only. So after solving this by using the calculator, we will get what, 26.57 degrees, okay. So this is the angle of transfer function at this location, okay. Now what will be the angle of departure? So we know that 180 plus angle of GH at the point's location is the angle of departure, and we will add this thing and 180 degree, okay, 180 degree and adding this thing, so what we will have, that 153 degree. So approximately what will happen here is, now drawing the complete root locus diagram for this transfer function, this was just a rough diagram, now drawing that again, and we have pole here, we know the pole location, I'm not writing that again, okay. What we have a 0 here, we have a 0 here, okay. So at k is equal to 0, what will happen, that this pole location will be as the original. As we will increase the k value, this pole will leave its original position by the angle of 153 degrees, okay. So this pole will depart from its original location by 153 degrees, okay, and will strike the real axis, okay, at the breakpoint's location. And as we know, root locus diagram is always symmetric to the real axis, so this will also be symmetric to this one. It's not, so root locus diagram has reflection property, that it will be symmetric about the real axis. So if this is 153 degree, then this will be what, minus 153 degree, okay. Now as k will increase, it will strike at the real axis after some point, and one pole will move in this direction and one pole will move in this direction, and at k is equal to infinity, these both poles will reach at zeros, okay. And initially it was k is equal to 0 when the poles and zeros location was its original location, okay. What if we reverse the location of pole and the zeros with each other, okay. So if this was 0, if this was 0, if this was a pole, if this was a pole, then the root locus diagram will be same, just the path will be reversed. So this pole will move like this, and after striking it will move like this and reach at these zeros. Then this angle of departure will become what? Angle of arrival. Okay, thank you for watching the lecture. Please share it with your friends, and please hit the subscribe button of the system, and we will go for, so this is at the, thank you for watching the lecture.